All right, so this is for all the would-be, could-be, might-be engineers out there, or just mechanics who want to, let's say, take their thinking to a new level, and not just any old level, but really an official level that's used in the industry. So we're going to talk about something called FEMA, Failure Mode Effects Analysis. I specifically want to talk about failure mode. So if this term doesn't ring a bell to you, that's okay. You probably understand the concept even though you might not know the word. A failure mode is a specific way in which something has failed. So if you think about a garden hose, right? A garden hose can leak, it can kink, it can stretch, it can collapse, it can maybe in the heat of summer expand. There's different ways that it can break. Things don't just break, they break in specific ways. And the specific ways that things break we call failure modes. So failure mode effects analysis is something that's done in a factory or in an engineering company where when they're designing something, they begin to think about, okay, how might this product fail? And we need to understand which failure modes are severe and need countermeasures. So as an example, let's take this tool. So this tool could become blunt, the shaft could bend, the shaft could break, the shaft could be separated from the plastic could separate and crack, and as I'm pushing with this tool, I could jam this spike into my hand. And so engineers will do failure mode effects analysis, and they'll try to figure out different ways that their product might fail, and then they'll have to decide the severity or the frequency of that failure and if they want to put in a countermeasure. So they might put like a metal cap on the end of this, kind of like this, specifically to keep the customer from shoving their hand into this metal rod or something like that. That's probably not a realistic example, but I'm just trying to keep it simple. And in a production facility where you're building a part much more complicated than screwdrivers like a car, you have to do failure mode effects analysis, not just for if a thing breaks, but if a process breaks. So if I grab the long screw versus the short screw and I run it into the transmission, is that a problem? Is there a big enough cavity? Or so did I just waste an expensive screw instead of using a cheap screw? Or does it poke a hole in the transmission, I get a transmission fluid leak, and then I leave my customer stranded on the side of the road? So engineers are using FEMA to prioritize the things that they're going to work on and to prioritize the sort of things that they're going to automate. So as an example, in a really critical process, you will have to take a barcode scanner and scan the long bolt or the short bolt to sort of prove that you've picked up the right bolt so that you don't run it into the transmission case. And the equipment that does the scanning and the checking all costs money, and so they only do that for the processes that are really serious. And so when you go through this FEMA process, at the end you'll basically assign a score to all the failure modes. So in this case, a fuel line, that's what I want to talk about today. Let's say you have a leaky fuel line, which is one possibility, or a kinked fuel line. Now, a leaky fuel line could be a safety issue because it leaks fuel all over the garage. Customer goes out to start their barbecue and you get a spark and you burn down the house. So this would have a higher number. For sake of conversation, let's call it 100. Whereas kinked means the machine's not going to start. That's going to really aggravate the customer, but it's far less severe. You're not going to get sued for that. So it might be something like 50. And you use this process to prioritize yourself. Now, there's one other thing I want to mention, and that's called the DFEMA. The D stands for design, and that means when you design something, you design it in a specific way so that it probably can't be misassembled easily, like using poka yokes where things can only go in certain ways. Or sometimes you will create what's called a designated breakpoint. So this is not an example, but I forgot to grab one before I came out here. So you notice how this shaft is a particular thickness, and then right here it thins out. So sometimes what manufacturers will do is they will design into a component a weak spot. Now that's not because they want it to break on you and they want it to you have to replace it. It's because they say, okay, if the customer misuses this and they start putting a huge load on this, it could break. And if it breaks here at the tip, it might really hurt the customer. If it breaks here at the back, it might be hidden by the cavity that this is slid into. And so we want it to break right here in the middle. So they'll thin down the material. It's almost like a mechanical fuse. Now, these are not examples of that. I just don't have one handy because you don't see designated breakpoints in a lot of common stuff around the house, but you do see it in shafts where they will neck down a shaft to a thinner diameter so that it breaks there and only there, and then the blades that the shafts are attached to don't go flying everywhere or something like that. So that's kind of where the D comes in. They design it so that if it fails in a certain way, or they try and design out failure modes by instead of, as an example, making like 2 fuel lines of the same diameter where they could be easily switched, they'll do 2 different diameters. Anyway, I say all that because I'm a nerd, but what I want to show you today, I was working on a steel string trimmer, and I had a weird issue, and it needed a carb because there was a mechanical failure in the carb, but after replacing the carb, it still had an issue, which I kind of thought it would because the issue with the carb wasn't really matching the symptom. And what I found is that this fuel line was collapsing. So this fuel line has like an inner and an outer, and I'm no polymer expert, but a lot of times this is true of fuel lines. I used to be responsible for fuel lines in the factory at Volkswagen. So normally you'll have an inner layer, which is designed to resist fuel. And that's what actually does the sealing. And then you'll have an outer layer for robustness and stability and structure, because to make the whole thing out of this inner layer might be too expensive. And if you make it all out of the outer layer, it might just degrade. So this is probably, this line probably has an inner and an outer wall, and certainly that's what it looks like, although it's hard to see from this perspective. But that's what you can see here, is you can see that the outer wall has degraded and hadn't yet led to a leak, but what that does is that allows this thing to collapse or partially collapse under suction from the engine and from the carburetor. So anyway, as I was taking this apart, it just kind of got me thinking, and I thought, well, you know what, that might be an interesting thing to show people and to kind of explain not just that fuel lines on engines can collapse, but that they can cause really weird issues, but also just get people thinking in the FMEA context. I'll just give you one more example. So you kind of just saw how I pulled and started to separate this. So I've seen coolant hoses where you get a small cut somewhere inside this inner layer, but not all the way through to the outer layer. And so the coolant leaks from the inside of this tube to the outside of this tube, and then travels along in between these layers and starts leaking at the end. And so you basically have coolant leaking out the end of a tube in between the 2 layers. And mechanics out there, you've seen these sorts of things before. I'm probably not blowing your mind on that. But for those of you who maybe haven't seen those things, instead of experiencing those things and and seeing them for yourself, you can also imagine them. And that's one of the things that an engineer will do, is he'll say, okay, how could this fail? It could leak, it could collapse, it could kink, it could be mismatched between the inlet and the outlet, things like that. So like I said, I was just working on this today. It got me thinking, and I thought that might be worth sharing. For those of you who haven't heard my story, I'm a mechanic who kind of worked his way up to engineer, you could say. I went through Calc 2 and chemistry and physics and linear algebra, but I never got my engineering degree. But I worked with a lot of engineers a lot smarter than me, and I worked with a lot of good mechanics smarter than me. And mechanics and engineers, they run into the same thing. The mechanic will say, yeah, the engineer didn't think about how the line collapsed. And the engineer would say something like, well, we didn't do a very good FMEA. So it's kind of the same topic, but with different language. And sometimes it can be exciting if you're more mechanically minded to just kind of peel back the curtain a little bit on what engineers do and how they think and how they overlook things. So, all right, pretty boring video, 9 minutes long, about fuel lines and DFMEAs, but I hope that was interesting to someone. If this kind of stuff really excites you, I'd encourage you to start, dipping your toes into engineering, whether it's mechanical or electrical or something like that. This type of thinking goes across the disciplines. And yeah, I hope you found that interesting. If not, that's okay. Let me know by giving me a thumbs down. And go check out a guy named the Post-Apocalyptic Inventor. He's an electrical engineer, very smart. You can learn all kinds of things from him, probably more than you can from me. And I hope you folks have a great day.